Hi everybody, and welcome to another video where we're going to talk about some other issues associated with isomers of organic compounds. I'm showing here on the page the two kinds of isomers, or the one kind of isomer, the two molecules that we talked about in a previous video, where we had the trans isomer and the cis isomer, and of course I referred to those more specifically as the Z isomer and the E isomer. So these two kinds of isomers, these are what are called diastereomers, to be more specific. They are the subcategory of stereoisomers that are called diastereomers. And they're diastereomers because they differ in the way the molecules are arranged in three-dimensional space, right? The green up and down, the greens on one side. So these molecules, of course, have the same formula, but they differ in the way the atoms are arranged in three-dimensional space. That's what makes them stereoisomers. What makes them diastereomers is the fact that they are not mirror images of each other. So I know it's kind of weird to define things in terms of what they're not, but that's kind of what we're left with. So today, we're going to take a closer look at these things called enantiomers that are mirror images of each other. So let me move my E and Z out of the way, and let me introduce these molecules here. So the key feature that you should first notice that these molecules have that the E and Z did not, and that is tetrahedral carbons, right? I've got a central carbon, sp3 hybridized, of course, and now I've got 4 groups off of it. And importantly, I have 4 different groups off of these molecules, all right? So I'm going to arrange the molecules like that so that you can see that with respect to each other, they are the mirror image of each other. If I took the molecule on the left and I had it look in the mirror, what would it see? It would see this molecule here on the right. This is exactly like our left and right hands. See if I can get my hands in there, right? My left hand and my right hand, right? They're mirror images of each other. However I hold them, they are mirror images of each other. So my hands are enantiomers. Just like these molecules, they are enantiomers of each other. So what we need in terms of nomenclature, in terms of naming, is we need a systemic way to clearly articulate that I'm talking about this molecule, if that's what I'm talking about, or I'm talking about this molecule, if that's what I'm talking about. So I need a way for my nomenclature to distinguish between these two types of stereoisomers, which are more specifically enantiomers. Now, let's confirm that they're enantiomers in that they are mirror images of each other, but they do not overlap. I cannot get them to superimpose. So, for example, I could hold these molecules maybe kind of like that. And you see how the whites and the oranges are lined up with each other, as are the blacks. But when I turn around to the back end, I see that the purple and the green don't line up with each other. So that's what I mean by them being not superimposable. I can get some of the atoms to overlap with each other, but I can't get all of the atoms to overlap with each other. So they're mirror images, but they're not superimposable. So now I need a way again to describe, am I talking about that one or am I talking about that one? All right, so I'm just going to take a closer look at one of the atoms, one of the molecules, to go through this nomenclature stuff. So here's what I'm going to do. I'm going to assume that the central atom, of course, is carbon, a tetrahedral carbon. The white is going to be a hydrogen. The orange is going to be bromine. The green is going to be chlorine, and the purple will be iodide. Okay, so I've labeled everybody in terms of a specific atom. Hydrogen, chlorine, bromine, iodine. Okay. Now, in order to determine what kind of isomer this is, I'm going to appeal to the same priority rules that we used for E and Z. These are the Kahn-Ingold-Prelog priority rules that were developed, probably about 100 years or so ago, maybe a little less than that. And so the way we assign priority is, of course, by atomic number. So with hydrogen, with its atomic number of 1, that's going to be the lowest priority group coming off of my central tetrahedral carbon. Okay, so that's the lowest priority. In terms of the highest priority, it's going to be this purple guy that we've labeled iodine. That's the highest priority. Then the bromine, which we labeled orange, is going to come in second, and the chlorine will be third. So then to determine which version of the isomer I have here, what we have to do is we have to look at the molecule in a very particular way. So hydrogen was my lowest priority group. It had the lowest atomic number, so it's my lowest priority group. And what you do then is you look at the molecule in a way such that that lowest priority group is pointed away from you. Okay, get the low priority group pointed away from you. So here I'm pinching the hydrogen in the back, as you can see, and I'm holding it such that it's away from the camera. Now, when you do that, you then have 3 groups left over. And so what we're going to do is we're going to rank the priority of the 3 remaining groups according to atomic number. So the purple iodine with its atomic number of, what is that? I believe it's 52. Let's bring over a periodic table. Right, so, 53. So iodine has an atomic number of 53, bromine 35, chlorine 17. So 1, 2, 3. So bring back my molecule here. So the iodide has the highest priority, bromine has the second highest, and then chlorine has the third highest. And again, that hydrogen that I'm holding away in the back is the lowest priority group. So I have 1, 2, 3. And so what I do then is I look at the sort of clockwise or counterclockwise arc that I would make as I go from 1 to 2 to 3. So you can see here I'm making a clockwise arc of priority. Highest priority, second, third. So I'm making a clockwise rotation. We would refer to that as the R, the letter R, enantiomer of this molecule. So just like we had E and Z for alkenes, I'm going to have R, and the other option is going to be S for the other enantiomer. So this is the R version of whatever we would ultimately name this molecule. I guess we would name it something like bromochloroiodomethane. All right, so this is the R enantiomer of that. Now, let me bring in its mirror image, and again, let me line these up so that we are convinced that we have mirror images, okay? So the one on the left is the one I've already played with, and we notice that created a clockwise arc from 1 to 2 to 3. Let's take a look then at its mirror image. So I'm going to do the same thing. I take that lowest priority group, which is hydrogen, and I hold it away from my perspective, away from, in this case, the camera lens. And so iodine, again, is group 1, bromine is 2, chlorine is 3. Now you see that is going in a counterclockwise direction. This is going to be the S enantiomer. So if I hold these 2 molecules in such a way that you can see their mirror images with respect to each other, you can see that the one I'm holding in my left hand, as I go from purple to orange to green, is going to be counterclockwise, and the one I'm holding in my right hand, as I go from purple to orange to green, is going to be a clockwise rotation. So this is R, this is S. All right, and so that's how we distinguish between the enantiomers. We look at the priority groups and see if they go clockwise or counterclockwise once we're looking at the molecule correctly. So the way to think about this is to look down that low priority axis and then see what kind of a counter or clockwise arc that you make. Now, there are a couple of key features to keep in mind in order for a molecule to have an enantiomer. So this molecule has this molecule as its enantiomer. And what we have is we have a carbon with 4 different groups on it. That's called a stereocenter. When you have a tetrahedral carbon with 4 unique groups, that's referred to as a stereocenter. And because the molecule has a stereocenter, it can have an enantiomer, and because it has an enantiomer, we say that the molecule is itself chiral. That's C-H-I-R-A-L, but it's pronounced with a hard K sound, chiral. So both of these molecules are chiral. This molecule is the enantiomer of this molecule, which is the, and this molecule is the enantiomer of that, vice versa, and they both have stereocenters, just so you get used to some of the lingo. Now, if you have a molecule that does not have 4 different carbons, for example, 4 different atoms, excuse me. For example, this molecule here, I've got a central carbon, central tetrahedral carbon. I've got a red atom, a blue atom, a white, and a white. So I have 2 identical atoms on my tetrahedral carbon. So then I wouldn't be able to assign a priority ranking because two of the atoms are the same. So I then won't be able to determine any priority between these two white atoms, between these two hydrogens most likely. So this molecule is not going to be chiral. Another feature of molecules that are not chiral is they have a mirror plane of symmetry. If you look right down this molecule, I can chop this molecule in half. I can have the left half and I can have the right half. So a molecule that has an internal plane of symmetry will not be chiral. So I'm not going to have to worry about any R or S stuff with this particular molecule. All right. The last thing I want to show you is a molecule like this. This molecule, as you can see, has hopefully two stereocenters. Okay. And I've just got to do a little rearranging of some models here to get to show you its enantiomer. All right, so hopefully you can see that these two molecules with respect to a mirror that might be here are being reflected into each other. So the features I want to show here, both of these molecules now have two stereocenters, right? So this carbon has a red, a white, a green, and then another carbon. So this tetrahedral carbon has four unique groups off of it, as does this carbon. And then, of course, its mirror image also has two tetrahedral carbons with four different groups. Now, as you can see, these molecules, again, they are mirror images of each other. Now I'm going to make something up. Let's say that that carbon is R and that carbon is S. Then if I looked at the mirror image, this carbon would be S and that carbon would be R. So if I have multiple stereocenters, its enantiomer would have all the stereocenters be the other version. So if that's R, then that's S. If that's S, that's R. All right, so that would be an example of a multiple stereocentered molecule and its enantiomer. Now, let me just do a little bit of quick rearranging here. I'm going to rearrange the atoms on one of the compounds. And I'm going to just switch the green with the blue here. And so now you see that these molecules are no longer mirror images of each other, but they still possess stereocenters. I've got one stereocenter, one stereocenter, one stereocenter, one stereocenter, but they're not related to each other by being mirror images. So if I have two molecules that have the same formula, that have the same connections, but differ in the way the molecule is arranged in three-dimensional space, these molecules are still stereoisomers, and they are still related. The relationship now, though, is that these are diastereomers, okay? They are no longer mirror images, but they are still stereoisomers. So I can have stereoisomers that are like E and Z. Those are one form of diastereomers. Or I could have stereoisomers that have multiple stereocenters. And if all the stereocenters are opposite, that gives me the enantiomer. But if less than all of the stereocenters are opposite, that's how I get diastereomers. This is a lot of terminology and a lot of structure types, so it's going to take a little bit of while to get comfortable with all the terms, but I wanted to show you examples of everything. So again, I have here molecules that are mirror images of each other. These are enantiomers. Okay, and then I have molecules that are not mirror images of each other, but they do possess stereocenters, and so ultimately this particular pairing would be referred to as diastereomers. All right, so that's it for stereoisomers, diastereomers in terms of EZ, or in terms of having, say, RR and then RS. And then we have our enantiomers, where all the R's get turned into all S's and vice versa. All right, so we'll do some more practice on this with some nomenclature, with some worksheets, and get down this RS relationship when it comes to isomers.
Here are a few examples of molecules with stereocenters so that we can practice R and S naming. You can see in this first one that I've got an OH group here. So this is an alcohol. That's going to be our highest priority functional group. So we're going to start numbering our chain right there, and we're going to get up to a 5-carbon chain. I'm not going to go through right now how to do the alkene E and Z isomer. Convince yourself that that is an E isomer. And let's focus in on this stereocenter right here, where we've got to figure out the R or S designation. So what we're going to want to do is we're going to figure out the priority of each of the groups on that carbon 3. Let's just for now, let's draw in this hydrogen, and let's draw in that this is a CH3. Okay, so our priority would be, we're going to look for what is attached to this carbon, and so we've got a carbon, and a carbon. We know at least that the hydrogen is our 4th priority group. So let's go out one more step from the first carbon and see this carbon is attached twice to a carbon, whereas this one is once and this one is not at all. So what that's going to give us is a 1 position here and a 2 position on carbon 4, and then the methyl is actually position 3. Now, what you're going to do in order to figure out R or S is you're going to think of this as sort of a steering wheel. The hydrogen that's pointed away from you, you always want your lowest priority group pointed away from you. Think of that like the steering column. And then we want to know which way is our steering wheel going to turn. Well, here you can see I'm going from 1 to 2 to 3. Okay, if I continue around, you can see that's a counterclockwise turn. So that means if I have our 4th group pointed away from us, that gives me the S isomer, so that I'm counterclockwise is always going to be an S isomer. So what you want to do is you want to put any E, Z, R, or S designations at the beginning of the name. So that's in the beginning of this one, we've got our 1E for our double bond, and we've got 3S for our stereocenter. And those are both in parentheses separated by commas. And now we're going to name the rest of the molecule as we normally would. We've got our 1 substituent, which is the 3-methyl. We've got to designate the 1 position for the double bond, so that's where we get pentene. And then we've got to again designate the 1 position for the alcohol. So I have to have 1 pentene, 1 all. And remember that counterclockwise is going to be our S isomer. This next one has a cyclohexane, and we can see that there are 2 methyl groups attached to that cyclohexane ring. So we're going to have a 1-methyl and a 2-methyl, and we could keep numbering around the ring, but there's nothing else really going on around the ring. Let's again show, okay, so here's our CH3, and then there's a hydrogen that is not shown going away from us. That's nice and convenient, again, because now that hydrogen is definitely going to be designated as position 4 when we figure out the stereochemistry at position 1, at carbon 1. So again, let's look at what's attached to this carbon 1. We've got this single carbon here, we've got this carbon which is attached to 2 others, and we've got this carbon which is attached to 1 other. So when we go ahead and do the rest of our prioritizing, we're going to call this one position 1, over here position 2, this methyl group position 3. Now again, we're lucky that our hydrogen is already pointed away from us, so our steering wheel is going 1, 2, 3, so we are going in a clockwise direction, so that gives us an R designation for carbon 1. Now, let's look at the second one. So here's our CH3, and now the hydrogen is pointing out at us. So that's going to cause a little bit of a problem, but nothing we can't handle. Let me just go in and erase a couple things here so we can kind of keep track of our numbers without getting confused. Okay, so that was for the first one, which was R. Let's go in and number our carbons for this second carbon, this position here. Now, we know again that hydrogen is the 4th priority. And now if you look at this one, you're going to see our first priority is here, our second one is in the ring as well, and our third one is that methyl group. So now, when you think about this, if you say, well, I'm going from 1 to 2 to 3, it looks like I'm going counterclockwise. But now remember, we are in the wrong place. The hydrogen is coming out towards me. What I ideally want to do is put that hydrogen pointing away. What I don't want to do is redraw this whole molecule just to get that hydrogen in the right place. So what I'm going to think about is this. The hydrogen is pointing out at me. I am on the wrong side of the clock. So if this looks to me like it's counterclockwise, if I were standing on the other side, it would look to me like it was clockwise. So be careful that you're aware of where your 4th priority group is. If it's sticking out at you, whatever the stereocenter looks like, you're going to actually name it the opposite. So this looks like counterclockwise, which would be S, but in fact, since we're on the wrong side, that's another version that's also R. Okay, make sure you can prove to yourself that you can see that we're standing on the wrong side of the clock in that example. Okay, so that means that at the beginning of this name, we're going to have 1R, 2R, and then all we need to say is 1,2-dimethyl cyclohexane. All we have to say. That's so funny. All right, so 1,2-dimethyl cyclohexane. Let's get into a really good one now. You can see in this one, again, you're looking for your highest priority functional group, and I've got right here an ester. I can see that attached to my ester on this side, I've got a propyl group, not too complicated on that side. And now I'm going to number this so that this is the 1 position, 2, 3, 4, 5, and 6. So at some point I know already I'm going to have hex, I'm going to have hexene because of this double bond, and since it's an ester, it's going to be hexene-08. And now I just have to figure out R and S designations for positions 3 and 4. Again, I'm not going to talk too much about the double bond. Convince yourself that it doesn't need an E or a Z. Think about that. All right, let's go first to this carbon 3 and figure out whether it's R or S. So the priority of my groups, I'm going to take a moment to draw in my hydrogen, which is not shown. The priority is going to be that hydrogen is the 4th priority. Chlorine would be first. And then I have 2 carbons, 1, 2. Okay, so this carbon, no help there. This is attached to 1 other carbon. This is attached to 2 other carbons. So that carbon 4 there is going to be my 2nd priority group. And then this one over here is 3rd. Okay, so again, let's look at what we're doing here. We're going 1, 2, 3. And again, it looks clockwise, but see here, my hydrogen is pointing at me. I'm standing on the wrong side of the clock. Again, you could redraw, but if you look at this and go, oh, this is clockwise, remember, we should be standing on the opposite side. So this is, in fact, going to be counterclockwise or S. So that's for position 3. All right, let's get rid of some numbers here so we can figure out what the carbon 4 stereochemistry is. Okay, so carbon 4 I have, let's draw in a couple of things. I've got this CH3. I've got this hydrogen, which is pointed away. That's good news. That makes it easier to tell what's going on. All right, and so we're going to put hydrogen as position 4. And then if you look carefully here, I've got this carbon attached to 2 other carbons, in fact 3 others, but this one's attached to the Cl. So my first priority is this one, my second is over here, and my 3rd one is the methyl group. So now you can see the hydrogen is correctly oriented away from me. I've got 1, 2, 3. I am going in a clockwise direction, so that makes this one an R isomer. So let's put this name all together. We're going to start with propyl, of course, as the beginning of the name of our ester. We're going to leave a space because it's an ester. And then we need to put in our S's and R's for the 3 and 4 positions. So we have 3S, 4R. All right, and now we need to put our substituents in alphabetical order. So that's chloro before methyl. So 3-chloro, 4-methyl. And then we still need to designate the position of that double bond. It doesn't need an E or a Z, but it does need to be known that it's at the 5 position. And then that turns into hexene. And then we've got an OATE ending for the ester. So hexene-08, the 5 for the ene. And then you could put in a 1 in front of the 08, but we don't have to do that. All right, so we've got 2 stereocenters in that one and nothing to do for the double bond as far as E and Z. Let's do one more where I give you the name and we write the molecule. Now, this, I would say, is going to be more trial and error than some of you might like, but there are a couple things that I try to look at. I'm first going to go here and I'm going to notice that this is an oct, so there's 8 carbons in my main chain, and I can also see that it's an octene, so I'm going to have that double bond, and what I like to see is that it's 5E. That seems like I wouldn't care one way or the other, but often when you draw your typical back and forth carbon chain, often that comes out to be the E isomer for the double bond. So let's start with 8 carbons in a chain. 1, 2, 3, 4, 5, 6, 7, 8. So there's my main chain. And now I want a double bond at the 5th position, so that would be right here. Now, if there's no other substituents on that, that's going to come out to be E, and make sure again that you can see that. Then I need at the 4 position an one, which is a ketone. At the 7 position, I need a phenyl group. And now here's where the trial and error comes in. I'm gonna say, let's draw that coming out. And here's my phenyl, everybody's favorite substituent, I am sure. Okay, and then same thing for the 3-methyl. I know that I have to make both of them S. I'm just gonna take a guess here and do that, and that'll be my methyl group. Now, that's everything I need for this molecule, and then I'm gonna go back and make sure that my stereocenters are correct. So the first thing I wanna do is draw in my hydrogen here and my hydrogen there. And now let's take each one in turn and number the priority of the groups around those stereocenters. So for this position 3 here, I've got a carbon, carbon, carbon. That happens a lot, but this carbon is attached to an oxygen. So that one's going to be priority 1 right there. This one has 2 carbons, so that's priority 2, and then priority 3, and of course the hydrogen is 4. So now again, this is nice, and I've arranged it this way kind of on purpose, in that I have my lowest priority group pointing away. And so if you can see here, I go from 1 to 2 to 3, I'm going in a counterclockwise direction. Hey, that's S. Look at that. It worked. I have 3S right there. That's an S stereocenter. Doesn't always work out that way, but that one we sort of lucked out. And you can see I put the hydrogen pointing away on purpose so that if it worked out right, I wouldn't have to change anything. Let's take a look at our phenyl group substituent here. So when you look at the prioritizing of these groups, the phenyl is going to be position number 1, the double bond is 2, the methyl group is 3, and of course our hydrogen is 4. And again, I've just deliberately put the hydrogen pointing away from me, but now the problem is when I figure that I'm going 1, 2, 3 with the hydrogen pointing away, I have accidentally drawn the R version of this, and what I wanted was the S. Easy to fix this. And again, only if you have a pencil, but make sure you do these things in pencil. Now, if this would let me erase. Okay, so now what I'm gonna do is I'm gonna switch it up so that my phenyl group is going away and my hydrogen is sticking out. Okay, and once I do that, then you'll see now that I am saying, it's still the same, 1, 2, 3, but you see now I look like I'm an R isomer, but because the hydrogen's coming at me, I'm in the wrong side of the clock again. So with that, even though it looks like R from the other side, that's gonna be our S isomer, and that's the one we wanted. So that is our final structure for the 3-methyl 7-phenyl 5-octene 4-one. Okay, go find a worksheet to practice this, and good luck.